A variety of methods, both active and passive, are available to isolate explosions to limit the damage they can cause elsewhere in the process. Here we look at these options and their appropriate application. Combustible dust and vapor explosions happen frequently in the processing industry. More often than not, the initial explosion will result in a secondary explosion with devastating results outside the vessel or throughout interconnecting ducts or pipes. Having a comprehensive plan to prevent an explosion from happening under normal circumstances and mitigating the effects of deflagration under upset conditions is critical to the safe operations of any facility facing this threat. The plan should identify where potential flame propagation exists and include a decoupling strategy to prevent this propagation from occurring. This video will discuss various explosion isolation options. For an explosion to occur, 5 elements must be present. 1. Fuel, i.e. a combustible dust or vapor. 2. An ignition source. 3. An oxidizing agent, which usually is the oxygen in the air. 4. Confinement, which results in pressure buildup during the incipient explosion. And 5. In the case of dust, dispersion into the airstream. Ignition control, proper housekeeping to remove residual dust, continual training of plant personnel on dealing with the dust explosion risk, and effective management of change for prospective alterations to the process or product are all critical to helping prevent an explosion from occurring under normal operating conditions. Unfortunately, abnormal conditions that result in an explosion can happen in any process line. Explosion propagation. The transmission of flame from one vessel to another through an elongated duct results in enhanced burning rates because of the turbulence created during propagation increases the mixing of fuel and air. The result can be flame jet ignition and pressure piling traveling to the interconnected vessel. This often causes a much more energetic explosion in the second vessel than in the source vessel. Explosion isolation. Explosion isolation devices prevent a deflagration in a process vessel from propagating through a connection, such as a duct, chute, or conveyor, to other equipment where it could cause subsequent explosions. The devices work by decoupling the flame propagation and pressure piling between the connected equipment. These isolation techniques generally are categorized as either active or passive. Active explosion isolation. An active system includes detection components and a control unit, as well as the isolation device itself. These systems work by decoupling the flame propagation and pressure piling between connected equipment. The National Fire Protection Association Standards on Explosion Prevention Systems, NFPA 69, recognizes a number of different explosion isolation techniques as suitable. The active isolation devices are either chemical or mechanical in nature. Chemical isolation. These devices work by rapidly discharging a chemical extinguishing agent such as sodium bicarbonate into connecting ductwork to mitigate flame propagation. This is accomplished through a pressurized extinguisher mounted directly to the interconnecting duct. Mechanical isolation. Options include a high-speed gate valve. Milliseconds after the valve's detectors sense explosion pressure or flame, the controls rapidly deploy a mechanical barrier, closing the valve's gate across the connecting ductwork. Due to their cost, high-speed isolation gate valves most commonly are used in applications where the deflagration dust threat involves a high-value product, such as a pharmaceutical dust that can't tolerate contamination from dry chemical extinguishers. Determining where the active isolation barrier should be located requires consideration of a number of factors, including the explosion characteristics of the dust, size of the duct, detection methodology, reaction time of the isolation device to fully create a barrier, and the reduced pressure in the source vessel. Computer modeling often uses these parameters to determine minimum and maximum isolation barrier locations for each specific application. Passive explosion isolation. A variety of passive devices can mitigate flame propagation. NFPA 69 lists the following options as suitable. Deflagration pressure activates the first three types of devices. Flame front diverters reroute the flame front from the atmosphere through an opening such as a rupture disc or explosion door to minimize the flame from passing through. These devices only are suitable for use outdoors in an orientation that enables safe flame ejection. Because they redirect but do not completely block flame passage, flame front diverters can't serve as the only means of isolation if the design intent is to completely stop flame propagation. Passive float valves have internal valve plugs that can move axially within their housings. If an explosion occurs, the pressure wave in the advance of the flame front will push and lock the valve against the internal housing, creating a mechanical barrier. These valves can be single direction and bidirectional. They typically are used only for light dust loading applications. Passive flap valves are mounted on the horizontal inlet of the protected vessel, with the interior flap plate held open by the process airflow. When a deflagration occurs, the pressure preceding the flame front causes the internal flap plate to close, creating a mechanical barrier to stop flame propagation upstream. A latching mechanism is required to prevent bounce. That could allow flame to pass. These devices also must have continuous monitoring for any dust accumulation that may occur, except when there's a documented risk assessment and appropriate internal inspection protocol and frequency that has been approved by the authority having jurisdiction. A rotary valve intended for use as an explosion isolation valve must meet certain criteria as listed in the NFPA 69. These include design strength suitable for the explosion pressures that could be reached, a minimum of 6 vanes diametrically opposed, with at least 2 vanes on each side of housing in the position of minimum clearance at all times, metallic construction unless otherwise tested, and to ensure no flame passage, external bearings as well as maximum allowable gap of only 0.2 millimeters between the internal flights and housing. The last three passive isolation devices, static dry flame arresters, hydraulic type liquid seal flame arresters, and liquid product flame arresters, are used specifically for combustible vapor applications and are not suitable for combustible dust explosion propagation threats. NFPA 69 provides descriptive requirements for the use and limitations of these devices. Every explosion isolation method, whether active or passive, needs routine maintenance. NFPA 69 requires inspection at 3-month intervals. This frequency can be modified based on documented operating experience in hazard analysis, if approved by the local authority having jurisdiction and the designer. Inspection records must be kept on file for a minimum of 3 years. Changes to the process can significantly impact the effectiveness of the explosion isolation method. Some factors that could compromise the explosion isolation system include a change in the equipment, product, or operating temperature or pressure, process flow, or airflow. It is critical to develop and adhere to the robust management of change policy for assessing alterations to the process or product that potentially could undermine the ability of the explosion isolation method to perform as originally designed. Determining a suitable method for a given application requires consideration of a number of factors, including the type of combustible materials being handled, the material's propensity for caking or deposits, the impact of the cost, and the ease of maintenance. Passive protection often is an attractive option. For a vessel with single, small diameter ducts requiring isolation, it's generally the least expensive choice, both in initial investment and ongoing maintenance costs. Post-explosion refurbishment usually is less costly and simpler than for active systems. Moreover, plant personnel typically can perform routine inspection of most passive isolation methods. Duct orientation, dust loading, airflow, and pressure drop will impact the efficiency of using passive devices for explosion isolation. Active explosion isolation is a more flexible choice than passive because it can be installed on ducts regardless of orientation or dust loading. The explosivity limitations for active systems generally are much broader than those for passive systems. In addition, because active systems provide no internal obstruction during normal operation, they don't pose pressure drop concerns. The initial cost for active isolation often is more than for passive isolation. The comparison is very application specific and depends upon factors such as process configuration and duct size. Active systems typically require more extensive maintenance than needed for passive barriers because more components, the detection devices, controller unit, and isolation barrier, chemical, or valve, must be inspected. All isolation methods have limitations, so it's critical the isolation method has been tested and approved for parameters for the particular installation. Work with an experienced explosion protection professional to determine an explosion isolation strategy that's best suited for your application.